is diazomethane part 3 and PPA. In diazomethane part 3, I will be dealing with the left out application part. In the application of the diazomethane, continuation of that, reactions in which nitrogen is retained, that is nitrogen is gained or retained. Okay, so here what happens here is, here what you have to take is, you have to do and estered reaction and estered synthesis. So what is and estered synthesis is in this what happens, the diazomethane will be acting as a reagent that will homologate the acid chlorides. It's one addition of one of the carbon atom from the diazomethane to the acid chlorides is known as your or and estered synthesis. Okay, so you are taking the acid chloride and then if you are treating it with the diazomethane, in here diazomethane is having the minus charge. Okay, this carbon ion will go and attack to the carbonyl carbon of your acid chloride, and once it will go and attack to the carbonyl carbon of your acid chloride, and this bond which is present between the carbon and oxygen will shift and make a charge. Once it will make a charge, at that time what happens, and you are getting this adduct formation. After this adduct formation, the charge will again go back and then this chlorine will cleave out as a good leaving group. Okay, the chloride gets cleaved out. After that, you are resulting in the carbonyl compound over here. Okay, and then this hydrogen which is attached over here, RCOCH2, this is your methylene group, right? So this group, one of the hydrogen atom is acidic in nature. So what happens here is, one more molecule of diazomethane, if you will treat it with that, at this carbon ion will abstract the proton from the methylene group which is acidic in nature, acidic proton. Once it will abstract the proton, at that time this bond will shift, make it as a charge as a minus, generating you as the alpha diazoketone. Okay, this will have the negative charge, that is your carbon ion is generated, which is known as alpha diazoketone. Okay, so this charge again back, so this will show you the resonating structure. This will abstract the proton and it will result in the diazonium salt formation. Okay, that is, it is methylating it. After that, you are forming the alpha diazoketone. Once the alpha diazoketone is formed, you are resonating and you are showing one more of the canonical structure. Okay, so here if you will see, the nitrogen group is retained over here. Okay, and you can do the resonance, and then after that this charge will come back and then this bond will shift. This charge will make one bond and then this bond will shift, make it as a charge, resulting you in this the canonical structure. Okay, and then the left, whichever the part is there, that is your diazonium salt is remaining. So this diazonium salt, the chloride ion which is cleaved out over here, okay, in the second step, so that will go and then the attack of this chloride to the methyl group with the removal of your nitrogen gas. Okay, resulting you in the alkyl chloride and the nitrogen. So here if you will see, what do you mean by Wolff rearrangement? So Wolff rearrangement is nothing but the alpha diazoketones which I have shown you over there, and that upon heating it will result in certain rearrangement. That rearrangement reaction is known as Wolff rearrangement. Okay, to give you the ketones, resulting you in the ketones. Wolff rearrangement is nothing but it is the alpha diazoketones on heating undergoes rearrangement to form an ketene. In that rearrangement is known as Wolff rearrangement. So you are taking an alpha diazoketone and then upon heating what happens, in the first step you are cleaving out as the nitrogen, generating the carbene atom. Once the carbene is generated, at that time this lone pair of electron again will shift, rearrangement is going to happen over here. This will shift over here as well as this will shift, make a double bond and then this R group will migrate and rearranges towards the CH group. Okay, so your this whole group will go and migrate, resulting you in the ketene formation. And then in the ketene, if you will take the ketene, if you will treat it with the water, alcohol and amines, at that time if you will take the water molecule, at that time you will result in the aliphatic carboxylic acid. If it is alcohol, you will result in the ester formation. If it is amines, you will result in the amides formation. Then moving on to next topic, that is your PPA. PPA is nothing but it is the polyphosphoric acid. Polyphosphoric acid, it is how the polyphosphoric acid is formed. So it is the polymer of the orthophosphoric acid. You can see here orthophosphoric acid is nothing but H3PO4. Okay, so many of the polymers of your orthophosphoric acid, it will join together to give you the polyphosphoric acid. It is the many phosphoric acid groups attached. So here it is moderately the strong mineral acid. It's what it is having the what is the speciality of this reagent is, it is acting as a dehydrating agent. Okay, it has the dehydration property. So what it does is, in the uses, it can either do the intramolecular and intermolecular acylation of various synthesis like heterocyclic synthesis and acid catalyzed rearrangement. So how you will prepare this? So you are taking the phosphoric H3PO4 phosphoric acid. It XML of that phosphoric acid is treated with the 2.2 x grams of phosphorus pentachloride. Upon heating, you will result in the PPA, that is your polyphosphoric acid. In the application part, if you will see, there is cyclization reaction which is taking place. Cyclization of aromatic carboxylic acids to give endenones, tetralones and benzosuberones. Okay, so you are taking the aromatic carboxylic acids. If you will take the aromatic carboxylic acid, if you will treat it with the PPA at 100 degrees Celsius, what happens here is it undergoes the intramolecular cyclization reaction, and intramolecular cyclization reaction resulting you in the endenones. Okay, and then if you will again treat it with the PPA, same starting material, but you will get the different products, and one product will be your endenone and next product will be your tetralone. I hope you know the mechanism for this cyclization. If you don't know, you can ask me. And then if you will take again with the biphenyl groups with the 2 carboxylic acid groups attached to that, and you are resulting in the two of the rings over here, that is the 2 endenones attached, the 2 endenones are attached, that is your or benzosuberones. And then moving on to cyclization of alcohols, next application is cyclization of alcohols. If you will see here, the whole molecule is there and then the OH group is there, that is your alcohol. If you will treat again here with the PPA, one molecule of the water gets removed, that is your dehydration which is taking place to form the cyclic ring. Here the alkene will go attack over here, and then there is a cyclization takes place over here. And then again moving on to next application, that is your cyclization onto non-aromatic moieties. So here again if you will see, there is a dehydration taking place over here, resulting you in the cyclic structure. Okay, in the heterocyclic compounds, if you will see here, at first this alkene has to go and attack to the carbonyl carbon and of your amide groups, and then once it will go and attack this, you will double bond will, one of the bond will shift, resulting you in the O minus, as followed by that mechanism with the removal of your water molecule, you will result in this product. Thank you. If you have any doubts, you can ask me in the comment box. Go through that mechanism, it is basic, so I am not teaching. Thank you.